All right. Good evening, everyone. Today I'm going to present this paper, the federated learning with only positive labels. So this paper has been published in ICML 2020, and this paper aims to solve an interesting federated learning setting, that is to train only with the positive data labels. So the most relevant application of this paper is perhaps the user identification or user verification network. So, all right, okay. So here is outline today. Before going to this paper, I will briefly introduce you the federated learning and the motivating examples. And after that, we'll go through the proposed algorithm. And this algorithm is claimed to be effective under the theoretical analysis and empirical evaluation. And finally, I will conclude this work. So to begin with, we know that federated learning is one of the most popular learning framework. And due to its client and server architecture, it easily to allow the server to access massive distributed data and train a high quality neural network using this distributed data. So in each training iterations, it takes almost three steps. In the first step, the server will distribute the global model to all these participating users. And then the user can receive the global model, use their own data to update the model, and then send it back to the server. And the third step, the server will gather the update from the large amount of users and to make sure that the training is effective. And in the next cycle, the server will again distribute the new model to all its users, so on and so forth. So the application to federated learning is very broad. For example, the next word prediction, the image classification, and the target detection. Such federated learning settings not only effectively train this model, but also preserve the user's data, on its own device, and hence protect the data's privacy. One special example in this paper is actually the user identification. So for learning-based user identification, actually it is highly used in our daily life. For example, we can use the face or fingerprint, voice print recognitions to unlock our phones, or sometimes we use the voice to command or interact with the smart assistant like Alexa and Google Home. So the special goal of user identification, or sometimes more rigorous user verification, is to learn the discriminative features among users. Say we have user A and user B, we want to learn the feature that user A is exactly different from user B. So however, we have a challenge because such information is usually humans' biometric information, such as face, voice. They're always sensitive. And such information should be protected and not easily shared with other parties. Because sometimes we have the public data set for face and voice recognition. The user's own data is still valuable because your own data is still required to improve the current model. So in this setting, we have multiple users, we have distributed data, and this data is sensitive. So it is actually very straightforward to employ the federated learning and address all these issues. So we now have a learning-based voice identification network. For example, this is the voice verification. So the low-level layers comprises input layer to accept the instance from the user. It has a feature extractor, and it generates an instance embedding vector. This layer should be kept on the user's devices. And on the other hand, the higher layer, for example, the label embedding matrix, it has some universal information from the population. So it is better to keep at the server. To clarify this, the X means the instance. In this case, it's a voice sample. And this G here is a nonlinear function, and it represents the neural network. The GX is its output. We say this output is the instant embedding vector because it is generated from the instance. And this W here, it has some columns. Each column is the label embedding vector associated with a specific user or user ID. However, in the further settings, the label embedding vector matrix, just like I said, cannot be shared with all the users. Once it's because once this vector is shared with the malicious party, it can easily fabricate a fake embedding of the target user, and the malicious can use this fabricated embedding to pass an authentication. So as a result, the server will only send one of the embedding matrix associated with the specific user to the user K. So here we have another challenge because the user will only train this neural network. Actually, is the feature extractor with his own voice data, the instance X, and his own label embedding vectors. So what is the problem in these settings? Let's first look at this loss function. We take the contrastive loss as an example. They have two objectives. The one is the positive objectives, that is the distance, the square of distance of the instance embeddings comparing to with the user's label embedding vector, and the other part is the negative loss, that is associated with the distance between the instance embedding with other users' label embeddings. So actually, this loss can be replaced easily by another other common used loss function, such as the triplet loss or the cross entropy loss. So we recap the user will only have his or her own G theta and WY. So it means he or she can only compute this compute the positive part of the loss function and leave this negative part uncomputed. So if the server directly average the model updates from this kind of settings, it will result in a trivial solution called the label embedding collapse. So what is the label embedding collapse? It is very easy. We can see we just set the W equals are all the same for all the users, and the neural network will learn to match this kind of label embeddings. So at last, we'll end up with all these label embeddings and the instance embeddings equals to one value. So in this case, the positive loss will be 0. So it seems it is the direction to be optimized. However, if we look at the negative part, it actually goes to the maximum value. So in fact, this trivial solution is not usable, and it only gives us the bad results. So based on this observation, we just simply want to avoid this kind of solution from happening. So the author tries to use a very straightforward method called strat out. That is simply to optimize this kind of positive loss and trying to add a regulation term to spread out all the label embedding vectors. So let's go to the algorithm part. They call their algorithm federated average with spread out. So in short, it's Fed AWS. Just like I mentioned, the basic idea is simple. They just want to make sure that the trained label embeddings is geometric separated. Based on this idea, they also use the geometric regulation term to regulate all the label embedding vectors. So this term is a summation of distance over all pairs of learned label embedding vectors. So we want to maximize the distance. So we want to maximize the distance between two different label embedding vector from different user. We will add a minus here since this is a minimization. So we want to maximize this distance. And we will put a hyperparameter v here to indicate this is the minimum threshold we can we allow. And we only
Chenpei, I have a question. So for the WC and WC prime, they are like embeddings for different class, right? So the C indicate the class, but for one class, we have multiple data samples, right?
Mm-hmm.
So this W is like a matrix, right?
No, this W is a vector. We do have multiple data samples, but
yes.
This is called in this paper they called it instance embeddings. That is the GX in the last slides. That they noted it as this one, and the W1 is a fixed value learning each run. So this is the target. This is the target that the G theta should be close to this target, and this target is a simple only one one-dimensional vectors.
Vector.
Yep.
Okay, it's like this embedding or this vector is like the correct answer. Just like the embedding of the right phase, right? So any other data sample in the same class should be close to this WC, right? So then we don't need to compare, at the data sample level. We only need to compare this somehow the representative vector here.
Yes, that's the story.
Okay, I got it. Thank you.
Yeah, that's almost all the story in this paper. So the federated learning cycle will be modified. So the user will send the updated feature extractor and his own label embeddings. That is the representative vectors to represent all his instance to the server after learning. So the server will average the model updates of the feature extractor and compute this regulation as the replacement of the negative loss computation. So that is the algorithm of Fed AWS, and to implement this algorithm and make it more practical, they need to fix two challenges. The first one is the hyperparameter v is hard to determine, and the second one is the number of users that is C in this equation can be really huge. We know that for the speaker verification data set, the Voxer Lab, they have 1.7 million speakers in the data set. So compute all the pairs of data of user is quite expensive. So the solution is to use a method called stochastic hard negative mining. So that is simply we choose a subset, randomly select a subset, and we only choose the top K closest label embeddings to take it into computation. And during this process, we can easily find the V to be the top K plus 1 closest distance. So we can make sure that this term will always be positive. So we can remove the disgusting max here and only consider the D here. And again, it's still it should be a minimization problem. So as we want to maximize the distance, we put a minus here. So we will have a simplified regulation term in this equation. We'll compute only the selected label embeddings in this subset. And they also use some, will claim this kind of simplification will not affect the overall performance too much. So there is a, now we know that this kind of regulation will work, and will draw the optimization away from the trivial solution. But the question remains here is how rare this method will be, and what's the overall performance comparing to the Oracle settings. For example, the softmax, and the server has all the users' data. So they use some theoretical analysis and trying to answer all these three problems, these three questions. The first one is they want to find the reason why a simple spread out will work. And then they find out that this kind of spread out is really close to the cosine contrastive loss. And the third one is they try to prove that the Fed AWS is related to the cosine, closely related to the cosine's contrastive loss. And here is the, since their core analysis is around the matrix called of distance, in other words, also link this distance with the error probability and the contrastive loss and their Fed AWS. So in fact, all these terms are consistent to each other. Let's talk about the reason why a simple spread out will work first. And here is the proposition. So if we assign this rho equals to the minimum distance on all the classes, and we just set this epsilon to be the expectation of the intra-class distance, we will have this kind of equation. That means the probability that the closest class is not the correct class will smaller than a constant. So to prove this proposition is very simple, because this probability is equivalent to compute the probability that the distance between the instance embedding with the true class embeddings are larger than half of the distance between the interclass distance. So by using the Markov inequality, we'll easily have this kind of equation, and this one will be a constant. If we look at this equation, it should not be too surprised, because it is very similar to the communication detection algorithm, and this one is close to the expression of signal to noise ratios. So if we look at this constant, the epsilon here suggests the intraclass distance. So by running a local training process, it will approach 0, since it is constantly optimized. But it gives us another. It also implies that we will, if any effort tries to increase the interclass distance, will yield a better result. That is, if we have a larger rho, we'll have a smaller upper bound of this misclassification error. So that's the relationship between the distance and the probability. And second, they give us the definition of the cosine contrastive loss. So again, the positive part is the square of the distance that belongs to one class, and the negative part is the distance of the negative pairs. So the cosine distance is also defined in this equation, that will be 1 minus the inner product of these two embedding vectors. So if we substitute this equation into the formal one, we will have the final expression of the cosine contrastive loss. So as mentioned, as this paper mentioned before, the distance is their most important metric, and it's not surprised that this loss is close to their proposed FAT AWS, because they also use the implied distance metric. So we just write down the FAT AWS objective, and we write down the cosine contrastive loss objective. But comparing them, we found the only difference between these two objective functions is in this red box. The first one is for their proposed method. They're using the inner product of the class embedding vectors. But for the centralized setting, cosine contrastive loss, they're using the data inner product with the other class embedding vector. To compare this loss, we will end up with bounded differences in this equation. And the first part is a constant. We do not really care about it because it doesn't affect the progressive result. And for the second term, the Rxy here equals to the Wy minus the g theta here. So since we are running several local optimizations of this, this term will approach zero. So we'll have a bounded gap between these two kinds of objective functions. So in other words, using federated AWS is in the federated setting with one class is equivalent to use a centralized setting of cosine contrastive loss. So that means their method actually can give us very close performance comparing to the Oracle settings. So here is all the theoretical analysis. So at last, we'll see their evaluation. The evaluation method they're using is the classification with one class settings. So they're using the data set in two groups. The first group is a smaller data set with a smaller number of labels, the CIFAR 10 and CIFAR 100. And for another group is a multi-label data set with multiple with lots of the number of labels. So they're comparing their methods with the baseline. The first baseline is they're trying to train only on the positive loss. And the second baseline is they're trying to train with the positive loss, but with the fixed, sorry for the typo, there should be, with the fixed label embeddings. So they say this is generated from the observation that we fix the label embeddings. This embeddings is not updated during the training process, so there's no way for this baseline to collapse their models. And the third baseline is an Oracle setting that is using the softmax function, and they can have all the information from each user. Their model architecture, they're using the ResNet as the backbone, and their embedding dimensions are also in two groups. For the smaller data set, they're using a dimension of 64 for the instance and class embeddings, and for a larger data set, they're using the dimension of 512. At last, the training setup for this evaluation, they use 4K labels and 4K users selected in each round. So here is the result on a small data set. We can, from this table, we observe that the training on a positive label will give us, only on the positive label will give us very poor results. This is because the model collapsed. So this one is actually cannot be used in practice. But we find it surprisingly good result for the baseline 2. That is, the label embeddings are actually fixed, not updated. Even these label embeddings are randomly chosen, they can give us a much better result comparing to the baseline 1, and a close result comparing to their proposed method and Oracle method. And we can also compare the Fed AWS with the softmax, and we find that Fed AWS is the best method comparing to all the one-class settings baselines, and they can give us nearly close to the Oracle method performance. So their method is actually very efficient. And they also give us the result for on the multi-label data set. You can see the statistic of this three data set, Amazon Cat, the Wiki, and another Amazon data set. You can see that the number of labels is much larger than the CFAR data set. As you can see, the observation is almost coincide with the observations on the small data set, but we find out that the only difference is the baseline 2. It fails in the Amazon 670K and the Wiki dataset. The reason behind is probably the number of class is too big, and their dimensions is not sufficient to make all these fixed embedding vectors to be separate with each other. So the baseline 2 will fail to face this situation. But comparing to baseline 2, the Fed AWS still give us the best results in the one-class settings. And we can see the Fed AWS is again close to the Oracle settings with comparing to softmax and sleek. So that is all the evaluation they run in their paper. Oh, okay. The hyperparameters selected here, they use k equals 10. That is the hardest negative pairs selected from the subset, and the lambda is the weight of the negative or the weight of the regulation term. So that will be all for the evaluation. And at last, I will conclude this paper. First, just recap of all models we have heard in the seminar and the last seminar. So the first one is the centralized one, share everything, and they learn from both positive and negative labels. However, it is not desired because they're sharing the sensitive information and cannot be done in the federated settings. In this paper, they propose the Fed AWS. They share only the label embeddings to the server. So the local training only requires the positive data and labels, and server will aggregate the feature extractor, runs additional spread out regulation. And in last seminar, we know that there's a work called Fed UV that will only share the model update, and it will not share the embeddings to other users or the server. So instead of the reasons behind the success of sharing nothing is they trying to fit the instance embeddings to the error correction code beforehand the model training. So it has ensured before training that the label embeddings will be separate. So that is the magic behind the Fed AWS and Fed UV. So here is the conclusion. This work study a novel learning setting. The Fed they can only train on the positive labels, and they propose this method without the negative instance and label pairs. This work also prove the strong geometric regulation can replace the negative sampling, and at last this method can achieve a near Oracle performance. So that is all for today's presentation. So any questions?
Any questions, guys?
Hi, Chenpei. Thanks for your presentation. I have some question about this paper. I think first, I appreciate your introduction part. It gives me a really good application, user identification. When I read this paper, I didn't think about this application. So Yeah, I think that's make much sense to me. But here is one one question about this algorithm. I
Okay.
noticed that you didn't mention how they generate the aggregate the W the class embedding matrix in the server. From their algorithm, they aggregate from each user, because every user only owns one positive labels, so they can select that class embeddings to compose to the embedding label embedding metric in the server. So my question is, if in more general situation, say we have non-ID, but not the extreme situation like here we only have the positive labels. So if in general speaking, we for each client they have several classes, that's the data distribution is extremely different from each others, but still they have several usable or several meaningful class embeddings. So in that situation, how can we generate this W, the label embedding metric, in this setting?
Okay, I got your question. So let me clarify why it's special in the user identification. Because for the problem you're mentioning is not about the user identification. It's just not that extreme non-ID settings. So this W is actually not that sensitive in this case. This W can be viewed as part of the global model, can be safely shared with all the users. So W can be updated as the as part of the global model. So it will the basic rule is to use federated average. It should be updated in this way. But I know if the data is non-ID, the question is the federated average may not be a perfect aggregation rule. So, but for the way how they aggregate it is to share the W along with all the models and use some other techniques to combat the non-ID problems. However, the special part in the user identification is this kind of W contains all the sensitive information. So in this case, our model will be breaking two parts, and only this part will be shared. This W will not be shared. Everyone can only have the access of one column that is belong to himself. So updating W will not be seen as the feature extractor. You will only it's just like a shelf, and everyone submits his paper on that shelf. So that is the W here. If we do the average among all data in the user identification, that doesn't make sense. But for the settings you are mentioned, it makes sense, but not good. So that's my answer. Yeah, the key here is this W. This W is almost has all the users' ID. So the only difference this one is not cannot be shared. That's it.
Yeah. So the label embedding here will not be updated.
It will be updated.
Fixed?
It is submitted by the user in each round. So yes, it's not updated by the gradient, but it is submitted by the because GX is divided by is derived by the user, and the current W is sent by the server. So at the user side, they will have current GX and W here. They will compute the positive loss. And with this positive loss, you can see here, you will update, it has W here, right? So if you have the gradient, or they have the part of the, is partially updated by the positive loss. So they will have some updated WY, and this updated WY will submit to the server, and it will be replaced by a new W. And in the next round, this new W will be sent back to the user, and we'll have a new W substituted. So it's still updated.
Yeah, I get this part. I mean, my previous question is like here because the client only has one label, and their classification head only have one label embedding that's important. So in this setting, they only sent that only meaningful label embedding to the server, and in the server end, the server will aggregate, collect all the label embeddings from every client to generate this W, and they do another optimization in the server to update this W from their algorithm. So my question is like, if we don't care about this a specific application, like here the user identification, in more general application, usually the user will have non-ID data instead of this only positive classes. So in that situation, from my understanding, I think still from the user point, there are some label embeddings for some classes are more important than others due to the local due to the local data set. And in that case, if we as the server, can we still select or some do some weighting, or different with the Fed average, we do some tricks or optimizations based on only several embeddings from different clans, not the whole, like the Fed average. We aggregate all the classification head and do the optimization. So my question is more like how in that case can we only pick up some important label embeddings to generate a better like here the metric, the W here, to help the local training or the global convergence?
Yeah, I got your point, and I believe some works on the federated learning non-ID settings, they already have this kind of algorithm, but I don't think it's really like this one. The reason is just like I said, first of all, the W for that settings is shared to everyone, and the question why the reason why the non-ID will hurt the performance is it's hard for non-ID users to reach a consensus. But in this one, they only blindly to strike out all the embeddings. The reason behind it is they only want every user to be separate. They have no consensus, and there's no ration. I will not say rationale. There's no. It's not as close as there were no place in the embedding space that one user or one class should be there. There is no such objectives such spot for each class. The only goal for this user identification is they want to spread it out. They want every class not be as far as possible. But if you, in some for the question you are mentioned, let's take the image recognition as possible. There should be a there should be a distribution or some spots or some location that the embedding vectors should be there. But for each user or for the different distribution, they do not agree, or they can hardly get a consensus. So that is the problem generated by the non-ID setting. So I think the way we try to alleviate this kind of problem is to add some terms, for example, at the server side, at the user side, but not as easy as this case. This case is just to spread out. It may have some can serve as a very brute force baseline, but I don't think it can be useful in all other settings. Actually, again, I think the application of this algorithm is kind of small, but it is the possible direction, I have to say.
Yeah, good. Thank you. Thank you.
Thank you.
Any other questions, guys? Well, if no, let's thank Chenpei for making this seminar like a talking about a series of several presentations focused on similar topic. That's very good. Okay. All right. Thank you.